Now let's have a look at ad hoc polymorphism in Haskell, and that's captured using type classes. Now remember what a type class is. A type class is a family of types. In Haskell we can define our own type classes and define which types are instances of which classes. We can then provide definitions of the overloaded operations that are associated with a class, and we're going to describe this now. There's one thing that I would like to emphasize here is that there are certain analogies with the world of object-oriented programming, but it's not the same thing we're talking about. A type in Haskell describes an interface. It's not an implementation. It's a description of the interface of a certain kind of value. Whereas a class in an O language is really a prototype object. If you instantiate a class in an object-oriented programming language, you get an object. But you cannot instantiate types, and you're not meant to instantiate types. And type classes are not classes. A type class is a family of types. So please, please, please do not try to push the analogy too far. There are several type class definitions in the Haskell prelude, and if we want to understand type class declarations and instance declarations, it can be quite instructive to look at what's in the prelude, because it's got several good and simple examples. An example would be the type class EQ. It's the type class of equality types. And to see how we can define that, let's see what the definition looks like. Here it is. We write class EQ of A, and we say that EQ has an operation. We call this a method, because this is a function that's specific to all instances of the type class. We call it a method. And we specify its type. The type is, well, give me a value of type A and another value of type A, and then the method, the equality function, will return a value of type Boolean. So if we read this type class declaration, it says that we're defining a type class EQ, and it has a method, or we have an associated operation, that if A is a member of EQ, well then the method will have type A to bool. Now what if we want to define instances of a type class? Here's an example. We could define that the type integer belongs to the type class EQ, and we do that by writing instance EQ integer where, and now we've said in the first line that integer is an instance of EQ, and we now define how the method is actually implemented for this particular instance. We say that x is equal to y if it's the case that x as an integer is equivalent to y. Now this operation, integer EQ, is written in back quotes because it's an infix operation. In this case, this function is a function that's predefined in Haskell. It's a primitive predefined function. But it doesn't have to be that, because in an instance declaration of the form instance, some type class and some type, where then whatever methods we're talking about, then this method is just a function definition, and you can write anything that you would normally write in a function definition. Because all you're doing is you're specifying how to implement the function that's a type class method. So you can write anything you would write in a function definition. Now we can define dependencies between type classes in Haskell. Here's a declaration of the type class of ordered types, and it says that if we have a class A that's a member of the type class EQ, then it's also a member of ord A, and we then specify the methods that are special to ord A, and these are the comparison operations, less than or equal, greater than or equal, and greater than. They're all functions of type A to bool, and we define maximum and minimum, and max and min are functions of type give me an A, and then we get back an A. But here the central notion that we're introducing is that we have this notion of implication, that if A is in the type class EQA, then A is also in the type class ord of A. So in other words, what this implication says is that every type that's a member of EQ is also a member of ord. And this is deliberately similar to the notion of inheritance that we know from object-oriented programming. We can have multiple inheritance. We could write something like class EQA, comma show A, then C of A, where ... This would be a kind of multiple inheritance, and we can do that if we want. So all in all, the language that lets us specify dependencies between type classes looks like a small fragment of propositional logic with implication and one might ask, could we use the full propositional logic for this? And it's something that's being looked at. It's not the case for Haskell, but one could imagine stronger notions of defining dependencies between type classes. We're not going to go into that here.